Welcome back, ladies and gentlemen. This is Mark Anderson for Kellogg Community College, and today we're going to look at simplifying radicals. We are first going to ask you, at the start of any of these pages, I would strongly recommend that you make a root chart. A chart of all the possible roots up to maybe 12 squared. So a root chart would be 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. Now, what this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and this is a really handy chart that I would continue to write down when you need it, because you're going to be looking at simplifying radicals today, because from in this chapter and in the next chapter, unless otherwise stated, you cannot take the square root of any non-perfect rootable number and give me a decimal. They have to be simplified. And what I mean is that most of the time, especially up to this chapter, you've been taking square roots of things that have been perfect whole number answers. You may not even actually understand what a square root is. A square root is actually looking at 25 objects, arranging them in a square, and then getting the dimensions of that square. That's what a square root is. The root is the length and width, that individual dimension that would make up a box that could contain that amount. So if I made a box like this that would hold 25 objects in the center, so if you count up these 5 rows and 5 columns to make a total of 25 pieces on the inside, this would create a box that's 5 by 5. So the square root of 25 is 5. The square root of 36 is 6. The square root of 49 is 7, and so forth. If your numbers aren't on this chart, they don't make whole number square roots. So take this example, number 2. The square root of 48 isn't on this chart. It's close to 49, but this could not make a square with a perfect whole number. It would make a perfect square with a decimal, close to 7, like 6.8 or something, or 6.9, but it's not a perfect decimal. But we do expect you to simplify these square roots for more simplified perfect answers. And what we will use is the property of square roots. The product property of square roots says that if a times b is under the radical, you can split that up into the square root of a times the square root of b. And I usually use this example of the square root of 64 is the same thing as the square root of 16 times the square root of 4. And by taking square roots of these, you can see that 8 is equal to 4 times 2. Now this is just an example of this property, but we can use this property to our advantage in asking ourselves, hey, what is the biggest number on the chart that can divide the 48 perfectly? And the biggest number on the chart that can divide the 48 perfectly is 16. So I can make this into the square root of 16 times 3, using this property of 48 is equal to 16 times 3, and then breaking that down to the square root of 16 times the square root of 3, using the second half of the property, and then making that 4 square roots of 3. That would be a simplified answer. On a graphing calculator, you can type in the square root of 48, get a decimal, and then type in 4 times the square root of 3, and you will get the same decimal. But this is the acceptable answer on the test, because we need you to simplify these radicals and not give me a decimal approximation. I also want to note that sometimes people take roots of these numbers and don't realize that they're actually not going far enough, or not actually going close to solving the problem, because I want to show you in this rectangle here a mistake people make if they choose a number that's not the biggest number on the chart. Let's say, for example, someone says, oh man, the square root of 48 is 4 times 12, so I'm going to break this up into 4 times the square root of 12, and now I've got 2 square roots of 12, and they wonder why they get the problem wrong. And they get the problem wrong because the square root of 12 can be broken again. The square root of 12 is the same thing as the square root of 4 times the square root of 3. So what that would give you then is 2 times square root of 3, which is 4 times square root of 3. So what's the takeaway from this is that you should always look for the number on the chart, the biggest number on the chart, to divide 48 evenly. You would never choose a number that was more than half of 48, because then it wouldn't divide it by 2. It would be a decimal. So you may want to try several of these before moving on. Like with 72, don't start from the bottom of the chart and dividing it by 4 or 9 or 16. Start at the top of the chart and see if there's a number that can divide it. In fact, 36 can divide the 72 twice. So by skipping a few steps here, the square root of 72 is the same thing as the square root of 36 times the square root of 2, or 6 square roots of 2. And if you tried smaller numbers, you would get a different answer, but essentially you would keep going until you get to this spot. I have had students say that in previous classes they learned about taking the number and dividing it by 2, dividing it by 2, and dividing it by 2, and dividing it by 2, but this, literally at this level, should be the way that you do it because it's quick and efficient. It's the quickest way to see how you can break it down. In number 4, we're going to look at the square root of 32 and see which is the biggest number that can divide it. And in this case, that would be 16. That negative 6 kind of sticks around a little bit and waits for everybody to get processed here. So this is the square root of 16 times the square root of 2. I prefer to have the number that's on the list in the middle or in front of the one that is not on the list, because that way I can just multiply it by the number on the outside. This is negative 6 times 4 times the square root of 2. Or the final answer would be negative 24 square roots of 2. And we will put our rational numbers in front, then our irrational number, or square root, radical, or any kind of root after the rational term there. So it will go rational, irrational, and then later on we'll put imaginary numbers at the end, like I, for example. All right, so you notice that the chart went away at the side of the screen, so I would hope that you would write down or look at your paper as you do these problems to use that chart as a reference. 3 times the square root of 144 is 3 times 12. Sometimes the number under the radical actually matches a number in the chart, so 3 times 12 is going to be 36. Here we have to break this down since the square root of 200 is not on the chart, but 100 is, and 2 would be its leftover, because 2 times 100 is 200. That would make this 10 square roots of 2. 88 can be broken down, but it honestly can't be broken down by a very big number. You can try all the numbers like 36, 25, 16, 9, but the only one that works is 4. This makes 4 and 22, or 2 square roots of 22, because the square root of 4 is 2. And then here we have 5 and 98. 98 can be broken, and it can be broken by 49 and 2. So this is 5 square roots of 49 times 2, or 5 times 7 times square root of 2, and that makes 35 square roots of 2. Now for the second half of your worksheet here, we're going to look at radical expressions, and for the rest of this worksheet, and probably for most of the chapter, we're going to assume that all values of x were raised from positive numbers. That way we don't have to worry about plus or minuses, and we're going to take care of that anyway when we get to the quadratic chapter in the next section of the book. But what we will do now here is talk about how do we do roots with powers of x on the inside. And there's a couple ways to look at this. One of the ways to look at this is that the square root is technically the index of 2. This is called an index, kind of like telling you what dimension you're in. So this is the second dimension, or square root. And this square root is asking us how many x to the sixths inside the square root can we let out. Now there's a property that I should write down, that if I have an index I'll call n, and then the x is raised to some power of m, well then this would give me a fractional power of inside over out, or inside over index. Now what I can do is then rewrite my problem here as x to the 6 halves. And you may want to try this on a calculator. See if you can take the square root of 25 and then write 25 raised to the 0.5 power. And if 25 is raised to the 0.5 power, you will see that the 1/2, or the inside 1 and the outside 2, does apply to the problem. So all of these are equivalent, 25 to the 1/2 power. So back to the problem up above. The inside power is 6, the outside index is 2, so x to the 6 halves is x cubed. But another way to look at this, using some previous knowledge from your work with mixed fractions, you can say like, okay, how many times does 2 fit into 6? And the answer is 3. So there's your answer. Now, sometimes you're left with a leftover. So how many times does 2 fit into 9? Well, 4 times with 1 left over. And that would be my answer here. This is literally x to the 9th power because I have x to the 4th from 2 fitting into 9 4 times, with 1 left over, x to the 1st power. Now, if you wanted to see it another way, you could have x to the 9 halves, which is the same thing as x to the 4 1/2, which then can be broken apart using the product rule, x to the 4th times x to the 1/2. And we learn from this rule over here that we would then have x to the 4th times the square root of x. And it goes to show you that this is a pretty important rule here, that x to the 1/2 power is the square root of x. Like, that's something you should memorize and be able to recognize, that if I do have a straggler like that, it would give me the square root of x. But I really don't mind which way you decide to process the problem. You can say, how many times does 2 fit into 9? 4 times, with 1 left over in the square root. Or you can go through the inside out. X to the 9 is on the inside, the 2 is on the outside, which is 4 1/2, which is 4 whole number, and the 1/2 radical to make the remainder, which is the square root of x. So for problem number 11, we're now going to have some whole numbers to deal with. So the square root of 16, that's pretty straightforward. That's 4. And now I say, well, how many times does 2 fit into 7? And it fits in there 3 times with 1 left over. Now what I'm going to do is give myself some space and write that 1 left over here, because I can now work with the y. 2 fits into y to the 10th 5 times with none left over. So problem number 11 is the way it is. Problem number 12, we're going to work on this whole number for a moment because 96 can be simplified if I break that down into the square root of 16 times the square root of 6. The square root of 16 is 4, and the square root of 6, I'm going to leave myself some space for x's and y's, and we'll put that over here because the square root of 6 cannot be further simplified. It's not a rootable number. There's no way to take 6 objects and make it into a square. 2 goes into 2 once with no leftovers. 2 goes into 4 twice with no leftovers. So here's my final answer. 4xy squared times the square root of 6. With 4 more examples to go, we're rounding the end of the video here, and we're going to go through this pretty smoothly. We're going to see that this x is going to wait on the outside and now process this on the inside. 2 goes into 2 once with none left over. 2 goes into 4 twice with none left over. So now I have x times y squared, which I can combine into x squared y squared. For problem number 14, I've got 4 times the square root of 36 is 6. And now I put my little 2 there to keep myself set when I have to deal with powers and other sections of higher degree, or index I should say. 2 goes into 6 3 times, so this is a cubed. And 2 goes into b 4 times with 1 left over. And there's my 1b. And we wouldn't put b to the first power there. That's redundant. We don't put 1 in front of x, and we don't put b to the first power. So now we do one more step of simplification. The 4 times 6, which makes 24. A cubed, b to the 4th, times square root of b. All right, so here I have the square root of 49, which is 7. And now I have this binomial, which is protected by the parentheses. And I ask myself, how many times does 2 fit into 2? And it fits in there once, which is just 7 minus 3 in parentheses. Now, if you did it the way that the book decides or wants you to do it, it would be x minus 3 raised to the 2 over 2 power, which is the same thing as 1. Now we will distribute the 7 to finish up our answer. And we're done there. Now, one thing about problem number 16, if you don't actually practice your homework, you're going to make some silly mistakes. I've seen students say, okay, 2 goes into this once, and this is 5, and I don't know what that is. I'll just say 5x, and Mr. Anderson will be okay with it. But I'm not, because this is a trinomial, and the trinomial is protected by these kind of silent parentheses that keep the thing in check. And the only thing we can do here, since these are all pluses and not multiplication signs, the only thing we can do here is try to factor and see if anything good will happen. Well, the good news is something really good will happen, because we're going to have two numbers that multiply to make 25 and add to make 10, which is 5 and 5. So that's x plus 5 and x plus 5. And now all my A plus students in the room are going to be upset, because instead of me saying keep them apart, I'm going to tell you to put them together. Because now we can say how many times does 2 go into 2? Well, just once, x plus 5. And you can write parentheses, you can write it without parentheses. It's a stylistic thing, but that is your final answer to problem number 16. And again, from this whole worksheet, we all assumed that these values of x were raised from positive numbers. That way we won't have to think about positive or negative values every time you take a square root. Because once we get to the quadratic chapter, we're going to pay very close attention when we take the square root of a number, because the answers could be positive or negative from there. But that's for a later video. Thanks again for watching this video on simplifying radicals.